Terminal velocity is sometimes called terminal speed. Why do objects fall at the same rate in the absence of air resistance? From Newton's second law, which is the sum of the forces is equal to the mass times the acceleration, we could rearrange that equation by dividing both sides by m to read the acceleration is equal to the sum of the forces divided by the mass. For a small object having a little mass, if we multiply that by g, this is the net force on a small object that's in free fall, m times g. In other words, m times g is in fact the numerator of this expression on the right. So to find the acceleration, we have to take the numerator and divide by the mass. So there we have it. And that's a certain acceleration in the downward direction. For a large object has a very big mass. We multiply that by the acceleration due to gravity. That is the net force on a large object in free fall. In other words, that is this numerator. But to find the acceleration, we have to divide that net force by the mass, and we get the same acceleration. Those two are exactly the same. So if you have a small mass in free fall, it's going to accelerate at a certain rate. If you have a large mass in free fall, just kidding. If it were in free fall, it would have the same acceleration as a small object, assuming air resistance is negligible. But what if air resistance isn't negligible? Air resistance depends on the geometry of the object and the speed of the object. You might have been driving in your car, and especially as a kid, and you hold your hand outside the window, and if you hold your hand one way, there's quite a bit of air resistance. If you flatten it out, there's not much at all. So the geometry of how you hold your hand very much affects the air resistance. Furthermore, how fast the car is moving greatly affects the air resistance. If you're in town going 30 miles an hour, there's not nearly as much air resistance as if you were to stick your arm out when you're going down the highway at 70 miles an hour. So, let's say we have a dove there at the top of a cliff holding an olive branch, and perhaps the best thing to do would be to shoot it. When we do that, the dove is going to fall. And if we assume that it falls from rest, there's a certain force, namely mg, the weight of the dove, that is accelerating it towards the planet's surface. If it starts with an initial velocity of 0, then there will be no air resistance on it. An object that isn't moving relative to the air has no air resistance force acting on it. That dove will begin to accelerate at 9.81 meters per second squared. Well, as it falls, it's moving faster. And as it moves a little faster, air resistance starts to build up on it, which means that there's a little upward force from the air resistance, because air resistance always opposes the motion, which means that the net force on this dove is no longer mg, but mg minus the air resistance. So he's still accelerating, but he's not accelerating at 9.81 meters per second squared anymore. You can imagine that as he goes faster and faster, at some point the air resistance will be exactly equal to his weight. And at that point, the dove doesn't stop falling, but he does fall at cruise control, which means he won't be accelerating anymore. He'll fall at a constant speed. And that speed we call terminal velocity. Because air resistance depends on an object's speed, the more mass it has, the longer it will have to fall before the air resistance equals the weight. In other words, the longer it will have the opportunity to speed up before terminal speed is reached. In general, then, greater mass means greater terminal speed. Ants do not have a very large terminal speed because they don't have much mass. They accelerate for maybe 10 centimeters, and after that first 10 centimeters of accelerating, they fall at cruise control, and not very quickly. Balloons are the same way. They have a lot of air resistance, and they don't have much mass. So if you were to drop a balloon, it would accelerate downward for a very short distance, and then from that point on, fall at cruise control. Beach balls would fall a little farther and accelerate a little farther, but even that terminal speed would not be very great. This medicine ball would have a fairly high terminal speed. It would accelerate for quite a long time before the air resistance underneath built up to equal its weight, after which it would fall at cruise control. You might have heard that if you drop a penny off a tall building and it happens to hit someone in the head before it lands on the sidewalk, that it could kill a person. Well, if there were no air, then maybe. Like on the moon. There's no air. Therefore things just keep falling towards the moon faster and faster and faster and faster. And I actually went through and looked up some information. If you drop a penny off the Empire State Building, it will hit the ground at an approximate speed of about 20 meters per second, because it will reach its terminal velocity. If you drop it into the Aitken Basin on the moon, which is about 6 kilometers deep, it would hit at about 140 meters per second. Of course, on the moon, there's no atmosphere, so there's essentially no terminal speed on the moon. That's not the case with the Earth. Terminal velocity occurs whenever an object is falling and there is resistance from the air or some other fluid. As a falling object accelerates due to gravity, i.e. its weight, it speeds up, which means the fluid resistance on it increases. At some point, the fluid resistance equals, and of course opposes, the object's weight, and the object no longer picks up speed. It falls at cruise control.